That parameterization is the key to everything we're trying to do. Remember last time we introduced a length parameter along the string, and that was called parameter S, and we had a vector dx ds, which is a vector along the string, tangent to the string, it's a unit vector. And we defined the perpendicular velocity to be the transverse velocity, dx dt, dx dt dot dx ds times dx ds. In terms of that transverse velocity, the action became minus t0 dt ds. You played with it yesterday, v perp squared over c squared. And t0 ds was the relativistic rest energy of a piece of string. T0 ds is the relativistic rest energy. So there's a couple of computations that have to be done that we need some results that are not hard to get, and they're just a little bit of work using this formula. Like, for example, I did not quite do the calculation to get this using this vperp and the Nambu-Goto action, but it's relatively straightforward, and I hope at some stage you do it. There's other things that are interesting, and one is that you, in this static gauge, now, I think I managed to confuse many of you, I apologize, with this word static gauge. Static gauge is a bad name. It's a gauge in which you say T is equal to tau. That's all it is. It doesn't mean that anything is static. Then I did an example of a static stretched string, and people thought, well, that's what static gauge is good for. No, static gauge is good for any moving string. It just makes tau equal T, and it's the end of the story. So in the static gauge, you can take the Nambu-Goto action, which is a Lagrangian, and calculate a Hamiltonian. And the answer is physically very simple and very interesting. The Hamiltonian is T naught ds over square root of 1 minus v perp over c squared. And that's the integral over the string. That's the energy of the string. And it's v perp squared. It's intuitively clear because if you have a string and you just want to know how much energy it has at any time, you consider a little piece and you say, oh, the rest energy of that little piece is T naught ds. That's the computation that we did yesterday. We stretch a string, you have a piece of string, it's T naught ds. And then there's the relativistic factor that we know has to go with some rest energy, and that you integrate over the string, that's the total energy of the string. This confirms that everything makes sense because you can calculate that h is given by this thing. Now, there is a couple more things. We wrote formulas, you remember, for p tau mu, which was dl dx dot mu, and p sigma mu, that was dl dx mu prime. And they were complicated formulas with the square roots and everything like that. But they start to simplify once you use static gauge and you write them in terms of the perpendicular velocity. So, for example, a few ones that are relevant are these ones. One that is relevant at this stage is that p sigma 0 is equal to minus t naught over c dx ds times dx dt over square root of 1 minus v perp squared over c squared. A pretty simple formula for p sigma 0. Why would we care about p sigma 0? If you remember the boundary conditions we were discussing last time, at every place of the string you would have that either a delta x or a p sigma, if any particular value of them, they all had to be 0, this product. So either you set this to 0 or this to 0. Now when we had the case x0, you cannot say that you hold the time fixed. It's not possible. The time always evolves. So you have to set this one equal to 0 for any string at the endpoint. Open string, free open string at the endpoint. So this is quite interesting, and we'll see now what it means. So if you have a free open string, so you have a totally free open string. All endpoints are free. To begin with, you must have that p sigma 0 at any time at the endpoints must be 0. It's one of our boundary conditions. So you look at it and you decide it's going to be 0 at the endpoint. So this thing must be 0. So that's a nice thing. Dx ds dot dx dt is equal to 0. Now, happily, that equation can be understood. You have the dot product of two vectors being 0. What do you know about these vectors? There's a great thing that there's an s here as opposed to a sigma. The sigma is a parameter, and dx d sigma, who knows what it is? It depends on your choice of parameter. On the other hand, dx ds is along the string, and it's a unit vector. So it's a non-zero vector along the string, and it points along the string. It says that at the endpoint, this is at the endpoints, this dx dt is orthogonal to dx ds, or maybe 0. So this is either 0 or orthogonal to that. So we'll say that it's orthogonal. Let's include things. So this is dx dt. And remember, at the endpoint, dx dt is the velocity. There's no ambiguity. You are at the endpoint, and if you don't change sigma, you remain at the endpoint, so that is the velocity. Dx dt is the endpoint velocity, and it is perpendicular to the string, because this dot product is 0 and this is along the string. So you've learned something very important, that at the endpoint, whenever you have a free endpoint, you will see it move it, and here is an endpoint of an open string. Well, it cannot move in. It always has to move perpendicular to the tangent to the string. Here is dx ds, and here is the endpoint must move perpendicular to it. So let's move on. I will call this relation alpha. Now, further things that happen with our simplifications of P that have to do at the endpoint. So when alpha holds, you have that P sigma. Now, I want to do the I values. we did the sigma 0 values. Now I want to do the I values, the spatial values. So I'll use a vector for this. Then it's given by this formula. Perp squared over c squared dx ds. So we're not deriving it, but this derivation is just a simple calculation. There's no logic that is complicated or anything. It's just a calculation. When you have a big formula for P sigma that we've written, and when you use this fact that this is 0, a few terms drop out, this is all that you have left. Now, this thing must vanish at the endpoints. And this is a unit vector again. So if it vanishes at the endpoint, the only possibility is that this factor vanishes. So V perp at the endpoints is C. And the endpoint must move with the speed of light. Yes?
In relation to the endpoint moving perpendicularly, does that mean that the length of the string cannot change?
You know, it doesn't mean that. It would seem to mean that. But here it is. I'll give you an example of an open string whose endpoint is moving perpendicular to itself, and the string is reducing. I'll show you one that's very cute. Here is a circle. Take an open string that is like this. And imagine, here's the center of the circle, that the open string at later times is doing this. The endpoint is moving perpendicular to the string at all times, and it's shrinking. So open strings can shrink. They do it in different ways than closed strings. So it's a little like your closed string that you used to have, but for an open string, this happens. Okay. We've done this, and when alpha holds, this happens, and therefore the string finally moves with the speed of light. This is the most famous result about open string motion. The endpoints move perpendicular, and the velocity of the endpoints is the velocity of light. That holds the string together. If you have a non-relativistic string that is supposed to have tension, and you release it, it just falls to the floor and does nothing. The relativistic string just keeps rotating and keeps doing things to keep the motion going. Okay. Further parameterization. We've done the tau parameterization. Let's do sigma. Further parameterization. Parameterization. We've drawn, you see, you should think in terms of drawing lines. We've drawn the constant tau lines on the world sheet. Now I want to draw the lines of constant sigma on the world sheet. And we're going to do it in a simple way. It's a physically intuitive way. Imagine the surface of a string. The string is moving in this room, and you see the surface. You see it with your eyes. This is not the space-time surface. You see the surface here. Well, it could be an open string. Let's imagine it's an open string. This sigma, this open string at the endpoint is always perpendicular to the velocity. So whatever you see here as this line developing is always perpendicular to the string at any time. So if you have the string at this time, at this time, at this time, this is always perpendicular. And this is the line of sigma, say, equals 0, and this is sigma equals sigma 1. And they're perpendicular to the strings. So the idea is to draw perpendicular things. So I will put, this will be, I pick a sigma arbitrarily. So I will pick sigmas arbitrarily on this first string. But once I pick a sigma, I draw a line perpendicular to this string, and then I know it's the same sigma here. And the same sigma here, always keeping it perpendicular. So you draw lines that always perpendicular to the strings, and they're perpendicular at the end, so this is all consistent, and you draw the sigma lines that way, keeping them always perpendicular. So our further parameterization is going to use, I'm going to write some words here, choose sigma equal constant lines to be perpendicular to the strings. So dx, the sigma times dx dt will be equal to 0. Let me clarify that. The x d sigma is a vector along a string because you're changing sigma. Remember, constant t, now those are our strings. So if you move along sigma, this is a vector along the string, Now the x dt, if you keep t constant, if you vary t, the x dt, you're supposed to keep sigma constant. So if you have t here and sigmas, the x dt is a vector along the line of constant sigma. This is along sigma constant. That's a derivative with respect to this. So therefore, this is 0 is precisely the statement that the lines of constant sigma are orthogonal to the strings. So this buys us something quite nice, because this dx d sigma is parallel to dx ds. The dx ds was also along the string, so you could put dx ds here. So this actually shows that at every point, you see your formula for v perp, the dx dt is now v perp. So v perp is now just dx dt. Because basically, you now chose sigma in such a way that this dx dt is along sigma is perpendicular to the string, so dx dt is v perp. At this stage, things begin to simplify even more, because you have one more condition. So your formulas for the p's simplify more, and we have not written the p taus. So let me show you what the p taus become. They will be important for us. P tau 0 now becomes t0 over c ds d sigma over square root of 1 minus v squared over c squared. And I don't put perp, but I could put perp if you wish. And p tau, the vector components for all indices I, is t naught over c squared. Again, this strange factor ds d sigma over square root of 1 minus v squared over c squared dx dt. Now, things are still a bit complicated, but we've made great progress. Okay. Why are things still so complicated compared to the non-relativistic string? There's this sigma and all this, and we have now drawn lines of constant sigma. So is there any freedom left? What can we do to simplify things more? Well, there's a little more freedom left. Why? If you remember what I was saying here a minute ago, I said draw the lines orthogonal to the strings. But the first string, you sort of have to choose the values of sigma. We have the lines, but we have not put the values of sigma on the lines yet. We have a little more freedom to parameterize the sigma. We know how the constant lines of sigma look, but we don't know what are their values. So we need to do some physics here that is related to the motion. So here is a claim. Suppose you have these strings, now with all these conditions that we've done, that the lines of constant sigma are perpendicular to this thing. Suppose you consider a point sigma and a very nearby point sigma plus delta sigma. Claim the energy delta E in the fixed infinitesimal delta sigma piece is constant in time. So basically what I'm saying is this. You have sigma, and you have sigma plus delta sigma, a little bit down the string. You're going to try to figure out how much energy there is in here. Well, you will find that that's the same energy that's in here, in here, in here, in here, as the string evolves. You've drawn these lines already. They're perpendicular. They're fixed. So you take two values, and you check that. So that's a claim. Let's prove it. So funnily, of course, the length here is changing. It could change. The length could change, but the claim is that physically, once you've drawn the lines that way, there's the same amount of energy on that little piece. Surprising thing, I think. So let delta S denote the length of this piece. And it's possibly time dependent. So what is the amount of energy in that little piece of string? From our formula for the Hamiltonian is T naught delta S over 1 minus V perp squared over C squared. So I will write it this way. I will say this is T naught, and the change in S is the derivative of S with respect to sigma that has been showing up there, over square root of 1 minus V perp squared over C squared. And so delta S is the derivative of S with respect to sigma times delta sigma. So the claim is that the amount of energy in that little piece of string is constant. Therefore, since this I take it to be constant, the claim is that this is constant. And that's a dramatic simplification if this is true. And how do we see that? Is this true? Well, consider consider the equation of motion of the string, dp tau mu d tau plus dp sigma mu d sigma equals 0, and take it for mu equals 0. You have dp tau 0 d tau plus dp sigma 0 d sigma must be 0. But p sigma 0, look at it. What does it involve? dx, ds, dx, dt up there. It used to be 0 at the endpoints, but now by our gauge condition is 0 everywhere on the string, because we've defined that the velocity is now perpendicular to the string. So dx, ds, dx, dt there is 0. So this term is identically 0. And therefore, dd tau is the same thing as ddt. So this is ddt of p tau 0. And p tau 0 is quite simple. It's this thing, t naught over c ds d sigma over square root of 1 minus v squared over c squared is equal to 0 by the equations of motion. And this is what we were claiming to be true. the claim is true. And now life finally becomes quite simple. We've almost gone to the end of the road in being clever with the parameterization. I just need to unpack what I'm going to do with this. This is supposed to be a number. So what I'm going to do is set the sigma, the S d sigma, over 1 minus v squared over c squared equals to 1. It's supposed to be a number. Maybe it's not 1, but if it's not 1, change the scale of sigma. All your strings are going to go from 0 to sigma 1. We'll make it twice as big. Make it such a way that this is just 1. And then, if this is 1, let's think physically what that means. It means that d sigma, from here, is equal to ds over square root of 1 minus v squared over c squared. That already tells you that you finally learned how to parameterize the string. Because you start with your string, and you say, sigma equals 0. Then you go to this point. You say, let's measure it. ds, how much is it? This much. Let's see how fast it's moving. That fast. Calculate the number. I know that this point is now sigma equals 0.01. And you can go along the string, and you mark the d sigmas, and you've learned how to parameterize it. We can do it a little nicer by putting a t0 ds, and 1 over t0, and the same square root. In which case, this is the little amount of energy. So d sigma is the energy over t naught. And this is probably something worth remembering. So basically, you're using the energy along the string to parameterize sigma. So suppose you have 100 ergs in that string. You go 1 erg, mark. 1 erg, mark it. It's a physical parameterization. No wonder it does good things. It's really using something important about the string. So, here, what happens now? Well, marvelous things happen. This p0, p tau 0 becomes a number, so we will not care about it anymore. And p tau, over here, this whole thing disappears. Finally, this whole thing disappears. So p tau vector is t naught over c squared dx dt. How about p sigma vector? We had it up there. P sigma vector, where are you? Here. It looks pretty close to it. Look at it. P sigma vector is minus t naught square root of 1 minus v squared over c squared. We have dx ds there. So let's do it with chain rule. Dx d sigma. Oh, and then for the chain rule, you'll have the s d sigma here. And that's 1 again. So this p sigma has become also very simple, minus t naught dx d sigma. Look how satisfying, in a sense. What used to be in the non-relativistic string pt used to be dy dt, and what was px was dy dx, and here is the same thing, the derivative of the position along the string. It's finally, if a free boundary condition is going to be the vanishing of this derivative, it's the Neumann thing that we've always liked. So this p sigma is good for us, and now look at your equation of motion of the string. We had it here, which reads dp tau vector d tau, which is t now, plus dp sigma vector d sigma equals 0. So what is this? P tau will be here t naught over c squared d second x dt squared minus, from the other one, t naught d second x d sigma squared equals 0, which is d second x d sigma squared minus 1 over c squared d second x dt squared equals 0, and you got a wave equation, a free wave equation. Now, this is great, of course. This is a very good progress because there was no hope whatsoever unless we did all this gauge fixing to get to this situation. But the relativistic string is not as simple as this free string because we have the parametrization condition. So there are extra conditions, like this one should be true. That you didn't have in the normal string. So let's see what are the extra conditions. So I will call, which is alpha ds d sigma. Yeah, this I will call equation alpha. And look what happens now. From alpha, I have that ds d sigma squared plus 1 over c squared v squared is equal to 1. Now, I claim, well, this 1 over c squared, this is dx dt squared. What is this ds d sigma? I claim this is just dx d sigma squared. Why? If you take dx d sigma, this is dx ds times ds d sigma. And if you square this, this is a unit vector, and you get the ds d sigma squared. So this is dx d sigma. So this condition must be true. So in addition to the wave equation, your parameterization condition, parameterizing with energy, means that that other thing, your derivatives, should satisfy this equation. And they should also satisfy dx d sigma times dx d tau dt, is equal to 0. These nonlinear conditions are the most famous conditions in all of string theory. They are called the Virasoro conditions. In the quantum theory, they will generate the Virasoro algebra. There are constraints on the motion. There are constraints in the quantum theory on the states of the quantum states of the theory. This is how this Virasoro thing gets born, and that's the intuition behind this Virasoro. In fact, there are two sets of Virasoro conditions here, because we can put a 2 here and add it here to factor this equation. We can put it with a +2 or with a -2, so these two equations get replaced by dx d sigma plus minus 1 over c dx dt squared is equal to 1. These two conditions are this plus minus here, and these are the Virasoro conditions. Any questions so far? We're pretty much, we've took us a little time, but we're almost done with the parametrization, the solution of the string. Yes? Yes.
So that is the same as always at that perpendicular position?
Right. When we said these things were perpendicular. Right.
Okay, this is the...
Yeah, it's the same condition. Any more questions? Yes.
So is there
Loud.
So is there parametrization as if we go to the local frame of rest, local rest frame, and take the proper length? Because if we, it looks like, wait, so it looks like d sigma is gamma ds.
This sigma is gamma ds, right.
So it looks like you're undoing the Lorentz contraction in a way?
I'm not sure. Yeah, I guess so. The Lorentz contraction. So the sigma is the un-Lorentz contracted variable. Yeah. Yeah, might have some meaning. That's a nice observation. Okay, so here is let's summarize this before we get to, let me see, I have to do this is the back one. I think I learned how to time myself. A lecture is going to be 6 blackboards, period. I stop when I run out of space. No, don't erase more. I think we'll do it this time, finally. Okay, so I want to summarize. How are you supposed to solve for a motion of a string? So here we go. We're going to solve for the motion of a string. So the whole set of equations. So you should look, summary. You should look at the wave equation. The x, the sigma squared minus 1 over c squared, the x, the t squared equals 0. So this is wave equation, WE. Then, once you solve this, well, you should impose the parametrization conditions. The x, the sigma, plus minus 1 over c, the x dt. Squared is equal to 1. This is a normal spatial vector that you're squaring and should be your length 1. And this is parametrization conditions. Then you must put boundary conditions. Now, we're going to do just free boundary conditions. And free boundary conditions means the vector p sigma 0 is always 0. That, it has to be free in time. So the vector p sigma must be 0. So the boundary conditions for free boundary conditions, that is the case we're going to look first, it will be just dx, the sigma at sigma star, which are endpoints, is 0. And you're going to have the string, say, going sigma belongs from 0 to sigma 1. Now, sigma 1 is something that we can keep track of. Although I'm going to write something redundant here, I think it's convenient to keep this equation over here clear. So I will write it like this. ds d sigma over square root of 1 minus v squared over c squared is equal to 1. But this is also equal ds multiplied by t0 and divide by t0. You multiply by t0, you get the energy, the sigma, times 1 over t0. Because the energy was this thing times this thing with a t0 and 1 over t0. So you have this. So from this equation, the energy is equal to t0 d sigma. You have that the total energy is going to be t0 times sigma 1. So the parametrization sigma is tied to energy. Therefore, if you know the length of the string in parameter space, you know its energy. Or conversely, if you know the energy, you know what parameter you should use to describe it. So the energy is tied into the parameterization. And this is a beautiful set of equations. Curiously, very few people looked at them. The only people that seem to know about these equations until year 2000 were people that did cosmic strings and Jeffrey Goldstone, who derived all these equations in the 70s to calculate motions of strings. And even then, very few people knew how to deal with this. So we're going to do our example. So here is the summary. For closed strings, things are a little different. You don't need a boundary condition here, but you have a periodicity condition. You will have to think about this a little in the homework. So let's do a free open string. Is there any question? This is the summary of what we've learned really in the last two lectures and turning the Nambu-Goto action into something usable.
Actually, I have one question. Sorry. So, especially in the beginning, I was thinking about, say, maybe we can introduce other degree of freedom other than the degree of freedom we introduced so far. For example, like, if just consider a curve, there might be some kind of like quotient. So the concept like that, maybe we can consider some kind of like, you know, Fresnel frame for a curve.
I see.
And you can have some kind of framing to make the string still have extra degree of freedom other than just the you know, area.
Okay.
So in that sense, maybe I was just saying that is there a reason why people don't consider that in the beginning?
Well, you know, basically, yeah, I don't know. It's hard. Basically, there's two things. Either whenever you try to put something, there has to be two reasons you do it. Either it sort of appears. So one reason would be if you're trying to do cosmic strings and you believe there's some other degrees of freedom. Like, for example, the string has, cosmic string may have large currents flowing on them. And if there's other interaction, maybe you add something to this thing. But in general, whenever you try to write something relativistic, it's very difficult to invent other things. Even if you succeed to invent something that more or less makes sense, if you try to quantize it, and it's very hard, people don't do it. So I think the answer to your question is that nobody has come up with something very simple. Now, we will put other degrees of freedom on the string. Eventually, you have x mu of tau and sigma. We'll put some fermions that depend on tau and sigma, as opposed to bosons, and we'll get superstrings, of course. But so there will be other degrees of freedom on the string. It's like this is embedded into space and into a superspace. But more intuitively, what people think is that the x's are two-dimensional fields. Those depend on tau and sigma. And these are more two-dimensional fields. So string theory is all about two-dimensional field theory, all the kinds of things that can live on a world sheet. And there are fermions, and there's supersymmetry in 2 dimensions. There's all kinds of nice things. So there will be a lot more degrees of freedom on the world sheet. And there will be gauge fields on the world sheet. A mu of tau and sigma maybe, or no, this would be AI of tau and sigma, because there will be 2-component gauge fields, and you can put all kinds of things, and maybe some torsion or some other. Okay, motion of an open string, free open string. How do you begin? Well, you solve the wave equation. The wave equation is not hard to solve, so let's solve it. X of tau and sigma is equal. You know how you solve the wave equation. It's functions of Ct plus sigma and functions of Ct minus sigma. So those solve arbitrary functions of moving to the right plus an arbitrary function that moves to the left. wave equation solved. That was easy. Well, we could decide to do other things. Typically, you could decide to go to the parametrization condition, but you should be a little afraid of it because it's a nonlinear equation for a vector, so that's tougher. So we go to the boundary conditions first. So for that, I need dx d sigma. So I do dx d sigma of tau sigma. And what do we have here? 1/2. You want to differentiate with respect to sigma. So we use this notation f vector prime, which means derivative with respect to the argument, ct plus sigma. And you differentiate the argument with respect to sigma, but that gives you 1. And then g prime, which is derivative with respect to the argument, and derivative of the argument with respect to sigma, that gives me a minus ct minus sigma. And this should vanish at sigma equals 0. So the x, the sigma at tau and 0 must be 0. And what do we get? I get 1/2 of f prime of ct minus g prime of ct. Equals 0. So what do you learn from here? Well, ct, well, f prime and ct, why ct? Ct can be any number, so really this means that f prime of u is equal to g prime of u, or I'll write it like this. G prime of u is equal to f prime of u. F prime is with respect to the argument, and then this is true for arbitrary argument because ct has any value. So g prime of mu must be equal to f prime of mu, which means that g vector of u must be f vector of u plus something independent of u, independent of the argument, must be a constant vector, a0. And now I learned, I'm sorry, no prime here, I integrated. Now if you differentiate with respect to u, you get this, and this is 0 because it doesn't depend on u. So I've learned that up to a annoying constant, g is the same as f. This is something that people that do open strings know. It's sort of the boundary condition at one point reflects the wave that comes in into a wave that comes out, and it has to cancel at the end. So these two functions end up being the same. Now, if I substitute here this whole thing, I would have f of ct minus sigma, and then I would have the a0 constant. The a0 constant is irrelevant because it's just shifting the origin. Or, in the best of cases, you could say you will have an f here, because it's the same, plus a0. And then you say, oh, split the a0 and a0 over 2 plus a0 over 2, and absorb this into the definition of f. That's another way of thinking that at the end of the day, what we have learned from here is that x of t and sigma is equal 1/2 of f of ct plus sigma plus f of ct minus sigma. And that's the whole thing. Now, there's so much here going on, but let's think of one thing that is interesting, is the following. If you could observe one point in the string for long enough time, you know what all of the string is doing at all of the times. Why? Imagine that you look at x of t 0 one endpoint. What is it equal to? The sigma and sigma vanish. So this is in fact f of Ct. So if you know what the endpoint is doing, you know the function f. And then you can reconstruct the whole solution. That's a nice thing. Okay, so now we go, rear goes to the top, middle goes here, and front goes here. Middle. Okay. Now, what else is missing? What should I do next? Any advice? Sorry?
Close.
No, close. I have not done with the open. We're not finished at all. I didn't solve the Virasoro condition. I didn't put the other boundary condition. We're far. It's like saying we should now do superstring. Okay, we can begin with a heterotic string now. No, we're still have to do simple things. So the other boundary condition, the other endpoint is also free. So what will that endpoint teach us? Let's see. So free at sigma equals sigma 1. So the x d sigma, now this is my new x, the x d sigma at sigma 1. So must be 0. So I get f prime of the first term ct plus sigma 1 minus f prime, I'm taking the sigma derivative, so that's why I did the extra sign, f prime at ct minus sigma 1 must be 0. Looks messy, but you know, all these things look messy to begin with, and you have to rethink them. So you call this u. It's just an argument. So then this becomes u plus 2 sigma 1. And then we've learned that this tells you that f prime, I'll continue here, f prime of u plus 2 sigma 1 is equal to f prime vector of u. So here's what you've learned now, that the function f prime must be periodic with period 2 sigma 1. Finally, the Virasoro condition. Okay, Virasoro. What do we do for that? Well, they are up there, the sigma plus minus 1 over c dx dt. And let's look at them. Well, so I have to write the formula. So dx d sigma is 1/2 of f prime ct plus sigma minus f prime ct minus sigma. And what is 1 over c dx dt? That's 1/2. Look, if you differentiate with respect to t, you get f prime of this things times c. That's why I put the c here. So you get here f prime of ct plus sigma. And now you don't get a minus sign because you're differentiating with respect to t. So you get plus f prime ct minus sigma. So if I add them and subtract them, I get dx d sigma plus minus 1 over c dx dt. If I add them, happily, these two terms cancel. If I subtract them, happily, these two terms cancel. So it's very neat. Things have been prepared to be very neat. So what do we get here? We get, in the plus case, we get a plus f prime plus minus sigma plus minus, like this. And that must be a unit vector. And this is an arbitrary argument. So what you've learned is that f prime of u times it's a unit vector. I'll say it in words, vector. So that's it. That's our end of the analysis. We put the two boundary conditions, the wave equation and the Virasoro conditions. And what did they get to us? They got this that you have to satisfy, this that you must satisfy, so I'm starring everything that you must satisfy, this and this is the solution. So the solution is this, with f satisfying two things. Its derivative, it's periodic with period 2 sigma 1, and its derivative, it's a unit vector. Not so bad. So let's do circular motion, the simplest case of a string, circular string. How is it going to move? I'm going to attempt to get a solution based on the idea that the endpoint moves in a circle. So you have a string over here. This is going to be L over 2, the radius. It's going to be rotating with some angle, so we hope it has some angular velocity, and the angle is going to be omega t. And let's see how it rotates. So we're trying to get the solution. So actually, look, this theory says if you know how one endpoint moves, you know the f, and then try to make it satisfy these conditions, and you got a solution. So I know how this endpoint moves. Let's write it. X vector of t0 is going to be L over 2 cosine omega t, comma, sine omega t. There's two coordinates involved, x1 and x2. So this is the first and the second. x1 and x2. So what is f from here? F, you basically read f of u is equal to x at the time u over c. If you put u here, t is u over c. So f of u is L over 2 cosine omega u over c sine omega u over c. And how about f prime? F prime, you get that with respect to u, you get omega over c in front. So you get L over 2 omega over c minus sine of omega u over c cosine of omega u over c. F prime is this, but f prime must be a unit vector. Well, sine and cosine make a unit vector. The squares are up to 1. So this must be 1. So we discover that omega over c times L over 2 is 1, or omega L over 2 is equal to c, which says that omega times the radius, which is a string of length L, the total string, circular string, is not circular string, it's circular motion, rotating string, rotating open string, rotating open string. So what is the length? The length of the string is L, and you see that the endpoints, omega L over 2, are moving with the speed of light. So this is, you wanted that. What else do we need for a solution? Only one more thing, this periodicity. 2 sigma 1 is the periodicity. So if the sine and cosine must be periodic with 2 sigma 1, you should have omega times 2 sigma 1 over c is a multiple of 2 pi. This is from the periodicity. This, maybe I should call this 1 star, 2 stars. So this is from 2 stars. Now you could put an integer here that is different from 1, and it would still be periodic. But actually, that would produce a string that is folded several times, something you can think about it. But this is the simplest thing. So from here, you get that omega over c is equal to pi over sigma 1. Now, why do I care about sigma 1? I care about sigma 1 because this will give me the energy of the string. Remember, the energy of the string is sigma 1. So I've determined sigma 1. I've determined now the energy of the string. In fact, the energy is therefore T naught sigma 1, which is T naught times sigma 1 is pi over omega over c. And omega over c is 2 over L, so you get L over 2 here. So you get pi over 2 L T naught. That's the total energy. It's a very important formula. E equals pi over 2 L T naught. Here's your intuition. If the string would be just stretch of length L, it would have energy L T naught. Because it's rotating, it has more energy. How much more? Well, different points. The result is a little more, 1.59 or 57 times more. That's the energy of the rotating string. The energy density is funny. It's lowest at the midpoint because it's not at the midpoint of the open string. The velocity is very small, but it's very high at the endpoints. It's almost diverging. So that's it. We're finished for today. We finished our first week. Have a lovely weekend. We'll see you on Monday.